Hey everyone, it's Mr. Ference. Today we are going to start our second unit of AP Physics 2 on thermodynamics. Our topic today is going to cover temperature, gas laws, and kinetic theory. So let's jump into it. The first topic I want to discuss is this idea of thermal expansion. When you heat up an object, it's going to expand. And so what we can do is if we look at this, we assume for now, just to sort of simplify things, that it is expanding in a linear direction. We have this length, this initial length, as it is heated up, it expands, and the difference between these two lengths we call delta L. We can determine what that length expansion is going to be by using this equation. It depends on the change in temperature, but it also depends on this other coefficient of linear expansion. This number actually just depends on the substance itself. I'm going to show you on this next slide a couple of different examples of the coefficient of linear expansion. You don't need to memorize these, you don't need to write them down, but these are the numbers that you would be plugging into an equation. Keep in mind, you can also see here that things will expand linearly, things can also expand sort of volumetrically, but we'll talk about that later. The main thing I want you to get from this is that the coefficient of expansion for glass, quartz, concrete, marble is much lower than the coefficient of expansion for metal. That is really going to make an effect if we have, for example, a glass jar where the lid is stuck. If you run it under hot water, generally that will loosen the lid of the jar. And the reason for that is because the metal that the lid is made out of, this aluminum, has a much higher coefficient of linear expansion than the glass that the jar is made out of. And so the metal will expand more compared to the glass, and you can unscrew the lid. The next topic I want to talk about is gas laws. So here, you don't necessarily need to write all of these down. We're going to sort of combine them all into one big equation. But if you remember back to chemistry, we talked about Boyle's law, where there's this inverse relationship between pressure and volume. This symbol right here means proportional to. So it is not mathematically equal, so I'm not going to use the equal sign, but I'm saying that pressure is inversely proportional to volume. So as the volume of a gas decreases, the pressure is going to increase. Another way to put this is that the product of the pressure and the volume will be constant. There are other gas laws that you talk about in chemistry. We have Charles's law, which tells us that volume is proportional to temperature. So as the temperature of a gas increases, its volume will also increase linearly. This is also where we get our concept of absolute zero from. If you sort of hypothetically trace this line past the y-axis, you go back all the way to the x-axis, it's x-intercept, so to speak. If there was a point where volume would be zero, where volume would be minimum, that temperature is what they call absolute zero. That is the minimum possible temperature. That happens to be at negative 273 Kelvin. And we'll talk more about how that works. But historically, this law, understanding this relationship, is where we have our concept for absolute zero. I think it's worthwhile pointing out here two things. In this unit, we are going to be using the Kelvin scale of temperature rather than Celsius. So the 1 degree Kelvin is the same interval as 1 degree Celsius. It's a 1-to-1 relationship. The only difference is that Kelvin is calibrated differently. So if you're jumping back and forth and converting, you just take your temperature in Celsius and add 273 to it, and we get Kelvin. For some reason, it's just Kelvin. It's not degrees Kelvin. It's just called Kelvin. I don't know why, but that's how it is. The other thing I want to point out here is that temperature has a very precise meaning in physics and in thermodynamics. We'll talk about sort of the philosophy and the math of how we can use this, but just keep in mind as we go forward, temperature and heat are different things. They do not mean the same thing. Temperature is just a measure of the average kinetic energy of the molecules in a substance. And I mean statistically average. They all have statistically random kinetic energies. But if we take the average, that's going to give us the temperature. So a higher temperature will correspond to a higher average kinetic energy for all of the molecules in the substance. They're going to be zipping around faster. So the other gas law that you talk about in chemistry is called Gay-Lussac's law. This tells us that there is a proportional relationship between temperature and pressure. So as the temperature increases in a gas, the pressure of the gas will also increase linearly. If we take these three gas laws and we sort of smush them all together, we find that they tell us important things about the relationship between pressure, volume, and temperature. If we change one thing, we're going to change the other. And so this is the relationship that we come up with. We get that the product of pressure and volume is proportional to temperature. So if one of these changes, the other one's changing. It might change proportionally. It might change inversely. Now I'm using this proportional sign. I'm not saying that these two things are equal. If we wanted to set these as mathematically equal to each other, there are some other numbers that we need to bring in just to make everything balance out. But we can do that. And what we end up getting is what's called the ideal gas law. This is the main gas law that we're going to be using in this unit. Just a quick rundown, pressure is measured in pascals. It's absolute pressure. Volume is measured in cubic meters. Temperature, T, is measured in Kelvin, not Celsius. The reason we're doing that is because if you have like positive and negative Celsius, that can mess up your math. So we just calibrate it. In Kelvin, everything is positive. The variable N here is going to be the number of moles of the gas. And then this other variable here, R, is a constant. It's just a number that we multiply stuff by so that it makes sense. You do not need to memorize this, but you will need to work with it in an equation. Another version of this gas law, this equation, we can use a different version. So instead of measuring the number of moles of a substance, we can actually measure the number of molecules of a substance. So that's the other version of this. PV and T are staying the same, but instead we're looking at the number of molecules. This other constant that comes in, we call it Boltzmann's constant. It is named after an old dead guy, and it is just that other constant R divided by Avogadro's number. Neither of these constants, actually none of them, including Avogadro's number, you do not need to memorize any of those, but you will be expected to use them in an equation. And in class, we'll look at some example problems where we are actually using these to figure out changing the pressure or the volume or the temperature of a gas and how that affects the other quantities. The other topic I want to talk about today is just a very short little footnote here. One of the difficulties in studying thermodynamics, for me at least, is that it's difficult to visualize this stuff. So we have this sort of mental framework that we can use to think about how this is happening. And that's a theory. That's really the scientific definition of a theory, is sort of a framework that we can use to analyze this. The theory that we're going to use to look at this is called kinetic theory. And these are its postulates. So these are basically, we're assuming that these statements are true. And as long as we assume these statements are true, we can use this framework and we'll get answers that match what we see in experiment. Really what we're looking at is that we have these molecules. You can actually imagine them as spheres just zipping around. If they're in a container, they will collide with the sides of the container. They will have collisions. They will bounce off and be moving around. So they're all moving in statistically random directions with statistically random speeds. Some of them are moving faster than others. We assume that they are far apart. and that the only times they're going to interact is when they collide with each other. They're not going to interact gravitationally or electrically or anything like that. They do obey the laws of mechanics, so we could, if we wanted to, use Newton's laws to study their motion and to predict what's going to happen. We're not really going to do that because that would be trillions of calculations, but if we wanted to, we could. We'll also consider these collisions are perfectly elastic, so kinetic energy is conserved as they bounce off of each other. As long as we make this assumption, as long as we assume that these things are true, we can think about this in terms of spheres zipping around and bouncing off of each other and the walls of their container, and we will still get answers that are consistent with what we see in experiment. So keep that in mind. So anyway, when we meet again in class, we will be solving some problems with the ideal gas law, and we will be looking a little more closely at how this kinetic theory works in terms of mathematics. So until then, take care, and I will see you soon.